So Solid Print 3D. Well, what we're going to be going through today is a guide to designing for additive manufacture. A little bit about myself to start off with. So I worked for Solid Solutions for several years before making the transition over to Solid Print. Must have been about a year and a bit ago. Outside printing, try my best to not fall off mountain bikes and rock climbing, but does happen far too often, must be said. Although not at the moment, keeping myself nice and safe. So a little bit about the company itself. So obviously Solid Print 3D, we're a sister company to Solid Solutions. So using a mixture of the facilities and the offices, as well as the engineers as well. With the plan basically to give honest and impartial advice on printers, making sure it's just the best fit for yourselves. So in today's webinar, what we're going through is just three main things really. So your basics of designing for 3D printing. So I'm going to be starting off just running through some key concepts, hopefully explaining how you can use them in current designs you've got if you're looking to use them for any 3D printing. We've got a nice example as well, which is one with the face shields that was being weird printing at the moment. And then lastly, we'll move on to a little bit further regarding the face shield and see how we can have more specific advice for certain printers. And also how SolidWorks can just quickly help just to get that design process tidied up and made nice and quick. So without further ado, so why 3D print? So you've got that comparison between injection molding and 3D printing is usually the most common. So it comes down to batches to start off with. If you're going over 10,000, injection molding does suit that quite well. Less than 10,000, 1 to 10,000 kind of range, 3D printing fits it. So that's that full customization you've got obviously over every single part you're printing. Doesn't really make too much of a difference. If your prints on the beds have got different text, different item numbers, whatever it might be. And obviously the startup costs are significantly less than injection molding as well. But how do we optimize a design for 3D printing? So we're going to start off, as I said, just with a few simple rules. So just to make sure everyone's familiar with the process itself, how do we start it off? Well, we've got to get the file. So inside SolidWorks is a nice and simple methodology. Just you've got your file, save as. You can choose your save as type to be an STL file instead. So there are other file formats can be used, for example, 3MFs, but STL is your standard. So you can see on that right image on the screen as well, effectively what it's doing is it's turning it into thousands and thousands of triangles. And that's what's building up the geometry that's then taken through into the slicing software. So your slicing software is going to be your middle ground. It fits between SolidWorks and the printer itself. So as soon as you've got this STL file, you're going to import it into the slicer. You'll have different slicers available for different printers, maybe an Ultimaker and Cura, Markforged and Eiger. But as soon as we've got that, that's when we can then basically give it the information for the printer. It's going to slice it up into a G-code, giving it all of the different layers it knows how to print. And we can see this is just a very quick little diagram running through the basics of an FDM or FFF 3D printer. Obviously, there are going to be slight differences between each one in the market, but your general workflow is usually the same. Gets filament, extrudes it, heats it up through that process, which comes out of a nozzle and creates, hopefully, the right looking object on the bed itself. But there's a few little different areas inside it we can, now that we understand the process, we can tweak and design accordingly for it. So let's have a look at some basic checks. So you've got three different options on this image here. So for example, the positioning of holes. So when we're going through and printing, if we've got holes in the Z going up vertically, they're not going to require any support if it's shown like in this image here. It's basically going to make sure that's going to improve the dimensional stability of it. Any support material that's going to be applied with it is going to obviously add an extra element on it, an extra element to the equation. We can reduce this if we can have your holes in the Z. It's only going to improve that process. So on that tag for B, your build plate adhesion. So your build plate adhesion is going to be how well the model is going to be printing and holding itself onto the bed. So I'm going to put back a slide just for a second, just so you can have a look at that nice little process again. So we're just having a look at the way in which G is interacting with H, how your filament is actually interacting with the build platform itself. If you give your models a nice flat base, it's going to give it the ability to lay it down and build up that first layer of extrusion correctly. Usually the most important the most important steps of the process with 3D printing is the first few layers. If you know they're adhering, if you know they're going down nicely, and as long as we design for it, it's only going to ensure that you're getting the best out of the print process itself. And C, we can see we've got a little cutout on the side, any areas that require support. So the term support I've mentioned a couple of times around this slide already. So the support material is going to be what's actually holding up the print itself in areas like that C where it might have some kind of material that's been removed, and the printer can only span so far. And this is something we're going to continue on the discussion with. So we can see these nice two images. 45 degrees is usually the rule that's applying to the supporting of the part itself. So on the left-hand side, we can see that this object's got an overhang that's less than 45 degrees from the horizontal, therefore it can support itself up. As each layer is building on top of itself to create the overall shape in this FDM or FFF process, it's only so far that it can stretch. If it goes too far, it goes past that 45 degrees, as we can see the image on the right, it's going to require support material. Otherwise, it's going to fall and you're going to have further issues from there. So that's why the 45-degree rule is usually the top one to go with. If we can incorporate that into our designs, we know we're going to get the best out of them because they're not going to require the support material, as I said, they can just build itself up. So kind of continuing on from that, how do you improve your designs, linking from the 45-degree rule onwards? So a nice way to think about it is the YHT rule. I said a continuation on from the 45 degrees. So we'll start with the Y on the left-hand side. Your Y is going to be the nicest to print out of those three letters in that orientation anyway. So because of the forks effectively coming up from the YR at 45 degrees in the horizontal at minimum, it can build on top of itself. It can print out that shape absolutely fine. However, when we look at the H and the T, most likely are going to be needing some support material. So for example, the H, depending on how far it's spanning across or bridging across in the middle, it might be able to survive. But if it goes past 5 millimeters, you're probably going to see some sagging occurring, and you're not going to get that kind of perfectly horizontal line as you expect with the H letter itself. So support material is going to be required. And T is very much the same story. If it does go past 5 mil when it's spanning out, it's not going to be able to extrude and hold itself in that position. And you're going to find that support material is going to be required. So these two rules here are probably the most simple, most basic rules you can find with 3D printing itself, or how we can design for 3D printers anyway. That 45 degrees and the YHT. So it's usually a nice way just to have a look at some of the models you already got and ones you're looking to be printing and think, well, how can we go through? How can we apply these changes to actually make the most out of the design process and the printing process? So let's think about this, for example, very basic looking cooling channel of sorts. As it is right now, it's just a circular extruded cut that's going through this. And we can see from the very crude image on the right hand side, it's going to require some support material. The sizing is too large, it's spanning past that 5 mil. So how can we design for this? How can we design for this printing process? Because at the moment, if you're trying to get that support material out of the end kind of side of that U shape, it's going to be quite difficult. You might have to create some different tooling for it. So if we can reduce the need for supports entirely, it's going to make our lives a lot easier. It's not only printing a lot nicer, but we're going to need less cleanup and less human interaction afterwards in the finishing and post-processing. So we could try and create almost like a teardrop shape. So this teardrop shape, we can link in with the 45-degree rule. We know, therefore, it's not going to require any support material, and it's going to print as it is. So we could try and make sure it's getting the same amount of volume of water pressure, air pressure, whatever it is that needs to be passing through this channel. So the exact same as to how it would have been with the circular profile beforehand, but this is now going to be self-supporting. As I mentioned, that post-processing side is also eliminated, as well as the need for support material. So two different ways we're kind of ticking off with that. So we've just gone through a couple of different examples. So we had a bit of a discussion about the YHT, bit of a discussion about 45 degrees. So let's have a look at the face shields that we are currently printing and accepting donations from many different companies across the UK, Solid Solutions and Solid Print customers. I just quickly mentioned on that, and I'll explain a little bit further. So the face shield designs are, we're using this RC3 design created by a company called Prusa. So these are being used for NHS workers, care workers across the globe. It's first started, and I believe the design itself was certified by the Ministry of Health in Czechoslovakia, I believe it was. So what are we doing with them? Well, we're printing on our own Cindo and Ultimaker FDM machines. We're accepting donations, as I mentioned, from customers of Solid Solutions and of Solid Print 3D. They're being sent to our Leamington Spa office, where they're cleaned up and then sent over to a local company called 3P Innovation, who are sterilizing them. They're packing them with the rest of the parts, so the elastic and the clear sheet, to create packs that are then sent out free of charge for care workers across the UK. So let's have a look at this design itself and see how this has actually been changed and tweaked slightly to make sure it prints nicely. So as I mentioned, this is the shield itself. So we're printing these top and these bottom pieces. So the top section is obviously connecting onto the individual's head. It gives a nice bit of a gap inside there so they can wear further eyewear underneath, maybe glasses or protective equipment. And then also there's a little lower bottom reinforcement section there as well. Again, let's think about that process I discussed at the start of this. You take your STL file, you then put that STL file into a slicing software, and then you print it. So the STL file can be downloaded, and if you would like to get hold of this file itself, please do let us know in the comments, and we can answer your questions and give you a link to where you can download it from. The slicing software, as I mentioned, will be usually different for each printer. So if you've got an Ultimaker, you might be using Cura, for example. You simply import it in, and then in the next few slides, we're going to run through some of the settings as well as the reasons why the design works so well for printing. So we'll have a look into SolidWorks in a couple of seconds, but firstly, we're just going to have a quick run through some of the reasons why it's going to work very well. So that 45 degrees again is popping up. So you can see different elements of the design itself have got 45-degree chamfers implemented into them in order to make sure that it is self-supporting. It doesn't need any support material, and it can build itself up nicely, getting the same kind of results every time. You're also going to find that by not printing supports, obviously it's not using extra material, therefore it's reducing the amount of reducing the cost aspect, and also the amount of material is being thrown away. Two other things, the build plate adhesion, well, it's got a nice flat surface, meaning it doesn't need any extra build plate adhesion tips and tricks, such as your brims, your rafts, and your skirts. And furthermore to that as well, it's not got any large overhangs. So it has got RC3 written in the side of them. However, I believe this is 0.75 mil. So that's obviously able to extrude itself absolutely fine, again, without the need for supports. As I mentioned, let's have a quick hop into SolidWorks and have a bit of a look through the design. I did show some screenshots there, but I thought it'd be nice just to have a bit of a run through as well. So we can see, as I mentioned, got a nice flat surface, top and bottom. So that's going to be the surface going to be printed directly onto the build platform itself. We've got all these elements inside here. We're going to have the 45 degrees, or as we can see here, an angle of 135. Obviously equaling the exact same. And we can spin the model around, you can see the same 45s in the back here. All of these sections, as I mentioned, all of these are just helping to make sure that it doesn't require any further support material. So you'll also be able to see there are some chamfers at the back. And what these allow the design to do is just to make it a little bit easier to take them off the build platform. If you do have any chamfers or any angles like this, it means you can get a scraper underneath just to get them off a little bit easier. So it runs into a slightly different aspect of the design, but it's also just making that whole process a little bit smoother, a little bit quicker, and a little bit easier. So as we can see, this is the full design itself. And I mentioned the RC3 in here as well. So it's just a small indentation, about 0.75 mil, which is enough to not need support material. So there we have it. That is the full design itself. So back across the PowerPoint and continue onwards. So we've gone through design. We've seen how it's used some of the 45-degree rules that we mentioned earlier. However, that's only half the battle. We want to make sure that we're printing these face shields to be as durable as possible. Obviously, they're going to need to withstand the stresses and the strains of delivery, as well as actually the wearing and the usage of them. They might be on the care worker's head for 30 minutes or 30 hours. So we can go through and we can use a few options actually inside Cure itself, which is what we're going to be using inside this example, or any of the different slicing softwares that are being used for the printing process. The two main ones that are really going to make a big difference are going to be the wall line count or parameters and the infill. So we can apply 30% infill, which is going to try and fill up the inside of the part itself with 30% worth of material. This can be changed into different patterns and different types. Won't make a huge difference for this example. I've just got it set to one of the default settings of triangles. And we've also got that wall thickness and that wall line count that I was mentioning. So obviously your wall thickness is going to be a multiple of the wall line count. So if your wall line count set to 3 in this example, which is exactly what we're going to be needing to get the durability, it's going to have that 0.4 nozzle on it, which has given us that end result. And hopefully you can see on the right-hand side a little image of exactly what you're going to be seeing inside the slicing software. We can run through and we can have a bit of a double check, which is something that I'd always recommend with the process itself. Making sure that we can actually have the right level of strength to the parts. This is something we can add into the design process. We can ensure that it's going to be able to have the ability to have this 1.2 either side and the ability to put a bit of infill in as well. I'll quickly just hop into Cura just so I can show you inside there as well. So we can see we've got these 3 wall lines either side and the infill in the middle. And this is fitting onto an Ultimaker S3, which fits onto the bed quite nicely. At this point in time, you'll be able to see if there's any issues as well regarding to having support material or not. We can use this just to run through and double check the exact amount of layers that are being put into the process. Obviously, there are many other different options inside here, but the main ones we've just discussed there are just regarding the actual strength aspect of the item itself, as we can see. All of these can be changed using these options in that top right-hand side, which you can expand out. And you can go into your shell, as I mentioned, ensure you've got the wall line count set to 3 and your infill set to that 30%. So we can see this is an end result showing on our Ultimaker S3. However, let's say for a slightly different purpose, we need to test and see how we can make the part a little bit stronger. At the moment, these face shields are being printed out of mainly PLA due to how easy and cost effective it is to print with, as well as other materials such as PET and PETG as well. However, let's say, for example, we wanted to do a slightly different design, and we want to just see how much strength we can actually get out of the item itself. So what we're going to do is we're going to see how we can actually reinforce the item with carbon fiber on one of our Mark Forge printers. So why carbon fiber? And what's the process around it is the next few steps we're really going to have a look at. So obviously you've got the CAD file itself to start off with. We're going to go through and slice and reinforce it in a slightly different slicing software, which is going to be called Eiger, which is specifically for the Mark Forge printers, and then to print it off with afterwards. If you're on George's webcast last week, you would have seen a couple of these videos, but it's always nice just to have a run through them again. So you can see this quick video here running through the amount of pressure that's being put through this chain link itself. You can see it putting up a massive amount of pressure through it, trying to get the failure. And there it goes. So £22,000, equal to 1 unloaded cement truck, 6 2009 Ford Tauruses, 19 Grizzly Bears, 1.6 T-Rexes, again, not quite sure I got the 0.6 in there, and 1,500 bowling balls. So that's the extra amount of strength we can hope to try and apply into the design itself. And it's a nice little stress strain, just if you're curious about the actual properties of the material itself, starting from your nylon, ABS, and onyx at the bottom. If you're unfamiliar with the Mark Forge printing process, onyx is actually going to be they're kind of one of their base materials, which is a mix of nylon and chopped carbon fiber. And then obviously you can go through and you can add in your continuous fibers, and that's where the strength is, the continuous fibers. Your Kevlar, your fiberglass, your high strength, high temperature fiberglass, and your carbon fiber as well, obviously. However, let's have a bit of a think back to the premise of this whole webcast. It's that designing aspect. How can we make sure that our models actually are going to be suited for the printing process? So we might have the right CAD, we might take it into Eiger, but what happens if our geometry doesn't actually allow us to add in that fiber reinforcement we require to get that strength? So we can see with the head shield itself, or the face shield, sorry, as it is, you can apply some amounts of fiber in, but it's not particularly going to be in the most effective of areas. So we are going to need to do a slight redesign. This is something obviously we can have a quick double check of inside SolidWorks. So we'll hop back to our face shield. I've actually preset up a different configuration inside here. So this configuration is going to have a slightly different thickness. There are many different tools we could use. So if you have got the SolidWorks file itself, obviously you go back in, you could start doing your redesigns. But with this example here, we are given the STL file. With the STL file, it comes in as a dumb solid, meaning that there's no real information around it. It's literally just going to be that file itself. So how do we go through and actually effectively do some quick changes to geometry? Well, the Move Face tool inside SolidWorks is probably the easiest and best way to do this. So within the Move Face, what I've actually done is I've taken these interior faces, as you can see. I've simply applied a 1 mil parameter to bring them all into the inside, as you can see with this lovely little yellow preview. So we're going to have a quick test and see if that extra 1 mil is actually going to make the difference. I've exported out this STL file and I've put it into Eiger to have a quick run through and do a double check. So let's have a check inside Eiger now. So Eiger is web-based, as you can see. You can get standalone versions as well. This is going to be where we're going to see the full process. So it gives a little bit of information regarding the part itself, and we can see it inside this 3D view. However, as I said, we want to double check and see about how the fibers are actually being put into the model itself. So I'm going to go down to the bottom right side and check our internal view. Our internal view, as you can see, is now showing the fibers inside our model. This blue pane across the bottom effectively shows how much fibers inside it currently, and it's literally just trying to put as much as it possibly can in. We can flip into a 2D view, and we can actually run through each individual layer. And you can see that build up in the areas shown here. It's only able to put in the fiber into these areas. As I said, the thickness just isn't quite there. So we added in that extra 1 mil all around these interior edges to give it a little bit more strength to it. So let's have a look at that. So this is our thickened version. That extra 1 mil. I'm going to hop into the internal view again. And now what we can see is actually able to apply the fibers all the way around, given the strength it requires. So we could go into a little bit further. We could apply some extra thickness into the top edges to make sure that we've got a fiber going continuously around the entire design. As we can see, it's actually encompassing the majority of it, giving it a lot more strength. Again, I'm going to hop into that 2D view just to run through and show you how it's actually building up these layers. So you can see it's literally just that one fiber loop going the entire way around, building itself up like so. So we might think that actually this amount of fiber is a little bit excessive. We can control this. We can use one of Mark Forge's design for additive manufacture theories, which is regarding their sandwich panel. So the sandwich panel works very similar to an I-beam structure, whereby if we have strength at the bottom, strength at the top, middle is not going to make as much difference to the overall design. So what I can do is I can go and I can actually remove that amount of material inside here from using fiber. Let it just go through and load that up. As you can see, it's just removing it off from the inside. We can see this live update from the left-hand side as well as it's going through. It's going to tell us the overall print time. This is going to be very much decreased because we're obviously using less material. There we go. So we knocked off about 2 and a bit hours, I believe it was. So currently it's using 2.9 centimeters cubed of carbon, as we can see. And again, that's something we can go through and we can do our changes and checks to. Other information gives us a vague material cost in dollars and also the final part mass. So let's quickly hop back across into the PowerPoint. I'm just going to run through the reason why that's actually occurred. Well, it's very simple. It's all down to the thickness, as I mentioned. We applied the extra 1 mil, and it took the general areas from being between 2 to 2.5 to around 3 to 3.5, with one of the lowest areas being 3.15. This allowed it to actually put in some fiber due to the theory, as you can see underneath. So the way that the Markforged printers actually work is down to whether or not it's an open or a looped continuous fiber. With the open features, you need a minimum wall thickness of 3.6 mil. When it's a looped feature, you can get away with having it at 2.8. So from this, we can actually go back in SolidWorks. We could do a few changes, as we know that we can actually get one loop round. If it's at 3.15, we could decrease that a bit further. We could reduce the amount of material, try and get it to therefore speed the print up a little bit further. All these changes we can do is all down now to the printer, rather than thinking about just the design itself. That's effectively what we've been trying to discuss throughout the entirety of this webinar. It's not just about the actual design itself, it's how we can think about the printer during this process. If we can add in 45 degrees in different areas, if we can think about maybe using a teardrop shape rather than just a straight circular cut, we can ensure that no supports are being required. If we are going to be looking to use a Markforged printer, for example, we could go in and we could just increase thicknesses slightly in some areas, just so we can put in that extra strength with the continuous fiber itself. It's been great having this conversation with you. I hope you've learned a few little tips and tricks you can use for your designs. If you have any further questions, please do let us know. Thank you.